Good morning, students. This lesson is from Chapter 8, Section 8.4, called the Binomial Theorem. And I'm wondering if this is possibly the first time you've ever learned about this. But we're going to learn how to use the binomial theorem and Pascal's triangle to calculate binomial coefficients and write binomial expansions. So I'm going to skip over the important vocabulary because we're going to cover that in the chapter. And I want to talk about what a binomial expansion means and what binomial coefficients are. So to do that, I'm going to go out to the side here. And if I've got a binomial and I want to take it to the 0 power, that is going to be equal to 1. And that's simply the definition of a 0 exponent. Anything to the 0 power is always 1. If we were to go ahead and do x plus y to the first power, we would get 1x plus 1y, or just x plus y. So, and we're going to be paying attention to these binomial coefficients because that is what this lesson is all about. The idea behind including this lesson in this chapter is we would like to remove some things from later in the course that are not as important, but this one is essential. There's a question on your final about it, and in general it has to do with noticing patterns. And anytime you can notice a pattern in something, then you've made a mathematical breakthrough. So I've written x plus y squared here, and if we were to expand that out and FOIL it, we would get x squared plus 2xy plus y squared. And if you're thinking about the coefficients, the first and the last have a coefficient of 1, the middle term has a coefficient of 2 and 1. Then let's get into some of the larger binomial expansions, x plus y to the third. I'm actually going to go, let me go down to the bottom of my paper where I have some room and just create a box so that I can keep track of my terms. I'm going to multiply x plus y times the quantity that I got for when I did x plus y squared, and that'll be x plus y to the third. So x squared plus 2xy plus y squared. And let me get another color. So x times x squared is x cubed plus 2x squared y plus xy squared, and then here we have x squared y and 2xy squared, and then y cubed. So the result for this one is x cubed plus, and then I'll look on my diagonals and combine like terms, 3x squared y plus 3xy squared plus y cubed. And that actually went off the page. Y cubed is my last term. Okay, so we're starting to get some patterns going. The first thing that I want to point out is that in each expansion, so this is, if we're looking at x plus y to the n, so here n was 0, n is 1, n is 2, n is 3. So in each expansion, there are n plus 1 terms. So in x plus y to the 0, we had 1 term. When there's to the first power, we had 2 terms. To the second power, we had 3 terms, and so on and so forth. In each expansion, x and y have symmetric roles. So you can kind of start noticing the patterns. Here you have an x and a y at the end. There's nothing in the middle for the first power, but now we have to the second power, we have an x squared at the end and a y squared at the end, and then in the middle they achieve this balance. And that's even more obvious in the x to the third power. We've got an x cubed at one end and a y cubed at the other end. And then in the middle, look what happens. We go in descending order of x, 3, 2, 1, 0. And we go in ascending order of y. There are no y's, 0, 1, 2, 3. So I'm going to put that under my general observations. So in each expansion, I'm not going to write that every time, x and y have symmetric roles. Powers of x increase by 1, no, decrease by 1, decrease by 1. Powers of y increase by 1 in each successive term. Another thing that we want to notice is that in the first power, the powers of your variables in each term add up to 1. So here the degree is 1, here the degree is 1. In x plus y squared, we have a second power, and then for xy we have 1 and 1, so that adds up to 2, and then y squared, that is a second degree as well. Then if you look in x plus y to the third, our degree is 3. Here we have a 2 and a 1, that's 3. A 1 and a 2, that's 3. And y cubed. So I'm gonna write that observation down as the sum of the powers in each term is n. And so if n is our power, then the powers are going to add up to n. And then we're going to go ahead and do x plus y to the fourth. And then I'm not going to do any larger powers, so I'm going to use this space right here to make a box. And I'm going to multiply x plus y times the result that I got from my x cubed term. So that's x cubed plus 3x squared y plus 3xy squared plus y cubed. And so inside the box, I'm going to put the results of my multiplication. I've got an x to the fourth over here and a y to the fourth over here. 3x squared y times x is 3x cubed y. 3xy squared times x is 3x squared y squared, and then xy cubed. And now my like terms are going to end up on the diagonals, so let me just write things in the same order. And y times 3x squared y is 3x squared y squared, 3xy cubed. So I've got 8 terms here, and then they're going to combine, giving me x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus, and I'm running off the page. So my last term is going to be y to the 4th. Let me just draw a separation here. Okay, so we can see that the patterns still hold. We have 1, 2, 3, 4, 5 terms in our x to the 4th. We have each degree adds up to 4. So here we have a 4th. 3 and 1 is 4. 2 and 2 is 4. 3 and 1 is 4. And y to the 4th is 4. So I just have one more observation to make, which I felt like was more obvious after the 4th time through it. The coefficients increase and decrease in a symmetric pattern. Now there's two ways to figure out what will be the coefficient, and the first way is by using the binomial theorem, and that states that the expansion of x plus y to the n equals, and then here's a general formula describing what you see in the different expansions. But if you look right here, this is a clue to tell you how one way that you can get the coefficient of any term, and that is by doing a combination of n things taken r at a time. And you maybe have studied that when you have been studying probabilities. Combinations of things are ways to choose items from a set without repetition. So let me show you what C with an N and an R in it means. And I'm going to just write the formula right here. That's n factorial divided by n minus r factorial times r factorial. And you actually have a button or a menu option to find n things taken however many at a time, and I need to be able to find those. Let's see, maybe it's in math, and it's over here in probability. So you see here you have this option right here, a combination of n things taken r at a time. This is where your factorial button is as well. So we're not going to get really into probability and statistics in this course, but we will use combinations for this purpose. Okay, so I had to play around with that button a little bit to make sure I know how to work it. So if we are doing a binomial expansion and we want to find the, let's see, the fifth term in an x plus y to the 12th situation, we're going to do a combination of 12 things taken 5 at a time. So that would be 12 factorial over 12 minus 5 is 7 times 5. So let me do that the long way. So I will do 12 factorial, and factorial is in math. That's number 4. 12 factorial. Don't be scared, it's a really big number. Divided by, and then I'm going to do 7 factorial times 5 factorial. And so we get 792. So that was the long way. But if you notice up at the top of my screen, I used my combination button. And so what you have to do is type in the first number first, 12, in combination. So under probability, that's choice 3, 5 at a time, and we get 792. So I want to talk for a minute about factorial. If you guys have never heard of factorial, the number 5 factorial, all that means is if you take 5 times 4 times 3 times 2 times 1. And so if I was doing a lottery drawing with a bunch of balls in the bin, and I wanted to know how many different possibilities for lottery numbers there were, I would say, okay, well, how many choices are there for the first ball? And there's 5 possible balls in the bin. And then after I take one out, there's only 4 left, so there's 4 choices for the next one, and 3 for the next, and 2 for the next. So if I did 5 factorial, there was 5 balls in a lottery drawing, then there would be 120 possible choices for the lottery. So that would not be a very good lottery with just 5 numbers, because people would be winning all the time, because if there's a 1 in 120 chance that you get the lottery number, people would be winning all the time. That's why in Powerball, I think there's, I don't know, something like 68 choices, and then you're picking 5 of them. So there's 68 times 67 times 66, 65, 64 choices. Now, to take into account for all the balls that are still going to be floating around in there, you have to say, okay, 68 minus 5 is 63, and then to take into account that you can pick them in any order. So that's where combinations come in. So this is actually the combination of 68 things taken 5 at a time. But anyway, I wanted to give you a little mini lesson on that. So what we're really concerned about, though, is writing out the coefficients for a binomial that's raised to a power, and that's called binomial expansion. And it's really easy what we did here on the side. You can expand binomials just by using FOIL if your power is not too high. But really, anything above a 4th power, it gets to be quite tedious, and the potential for making a mistake is pretty big. So we want to practice using binomial expansion in order to expand out this binomial, x plus 2 to the 5th. And I want you to notice, instead of a y over here, we have a 2, which, so just using the y to the 4th in our x plus y to the 4th power, instead of a y to the 4th at the end, 2 is now y. So you would have a 2 to the 4th, or a 16. So a lot of these are going to be replaced with numbers instead of variables. So we're going to use a binomial expansion method instead of multiplying everything out. So here's how it's going to go. We're going to have our x is going to be to the 5th in the first term. Then I'm going to have, in my first term, 5 things taken 1 at a time. So that's a combination, another combination notation. And then times x to the 4th. So I'm going in descending order of this variable, and then I'm going in ascending order of whatever the second thing is. So I'm going to have a 2 here. Then I'm going to have my next coefficient. Then I'm going to have x to the 3rd, and then 2 is going to be 1 more power, so that'll be squared. And I'm going to have 5 things taken 3 at a time. That'll be x squared, 2 to the 3rd. 5 things taken 4 at a time is x times 2 to the 4th, and then my last term is 2 to the 5th. So let's start working out what some of these numbers are. So let me do a combination of 5 things taken 1 at a time. And I get 5 there. So I've got x to the 5th plus, I've got a 5 and an x to the 4th, and I still have this 2 right here. I will need to combine the 5 times 2, but let me go ahead and write things out. So now 5 things taken 2 at a time. Let me go ahead and figure out what that is. Hold on, I need to go 5. And for that I get the number 10 times x cubed times 2 squared, which is 4. Now I'll do 5 things taken 3 at a time. Well, interesting. That's also 10. X squared times 2 to the 3rd, which is 8. 5 things taken 4 at a time. That's going to be 5 again. And then x is to the 1st power, 2 to the 4th is 16, and then 2 to the 5th is 32. So let me go ahead and just combine my multiplications here. So I have x to the 5th plus 10x to the 4th plus 10x to the 3rd, plus 40 x to the 3rd plus 10 times 8, 80, x squared plus 5 times 16 is also 80, x plus 32. So this right here is the binomial expansion of x plus 2 to the 5th. So a long time ago, a mathematician named Blaise Pascal noticed some patterns in these combinations, which you probably did too. You noticed that they go up and down in a symmetric pattern. So he created Pascal's triangle, which is sort of a summary of all of those coefficients. So I want to go ahead and construct rows 0 through 6, and that's going to correspond with the coefficients of the binomial expansions. So recall that x plus y to the 0 power equaled 1, and then, so let me write that out. And then x plus y to the 1st, our coefficients were 1 and 1. In x plus y to the 2nd, we had 1, 2, and 1. X plus y to the 3rd, we had 1, 3, 3, 1. X plus y to the 4th, 1, 4, 6, 4, 1. And then we did x plus 2 to the 5th. So let's talk about what our coefficients were. We had 1, 5, 10, 10, 5, and 1. So this is the first 1, 2, 3, 4, 5, 6 rows of Pascal's triangle. But I want to show you that you don't really need to know what the binomial expansions of these things are to get your rows. All you have to do is, if you start with a 1, and then for each successive term you're going to add together the 2 terms that are triangularly above it. So that's 20, 10 and 5, that's 15, 6, and 1. So the 6th row starts out with a 6 and ends with a 6. So I'd like to do one more problem using Pascal's triangle to get our coefficients. And so Let's do this example. 2x minus 3 to the 4th. So automatically when I'm doing a 4th binomial expansion, I know I'll end up with 5 terms, and I'm in the 4th row of Pascal's triangle. So these coefficients are just going to replace those combination numbers. So I'm going to start out with my first term, 2x is going to be to the 4th power. Then I'm looking for a coefficient, and 2x will be to the 3rd, and then my y will be to the 1st. Then in my next term I need a coefficient, and 2x squared, and my y term squared. Then I need a coefficient, my 2x term to the 1st power, and my y term to the 3rd. Then my y term will be to the 4th. So now I'm going to fill in the blanks. I could either use the combination function if I don't have Pascal's triangle handy, or I can just fill in. So this was 1, this is 4, 6, 4, and then that's a 1 again. So now I can, I have my binomial expansion mapped out, and I can go ahead and do the calculations. So 2 to the 4th, x to the 4th, that's 16x to the 4th. Now here I've got 2 cubed, which is 8, and a negative 3. So I've got to do 4 times 8 times negative 3. And so for that I get 96, and it's negative, and there's still an x cubed term. Then here I have a 6 times 2 squared times negative 3 squared. 6 times 4 times 9, so 216, and then there's an x squared in there. So notice when we have a negative right here, our terms are kind of alternating based on whether we have a negative power of, or an odd power of the negative. Okay, so in my next term I've got a 4 times 2 times negative 3 cubed, which is negative 27. So that's negative 216. And I've still got an x. And then negative 3 to the 4th is a positive 81. So this is the binomial expansion. Sorry for the long video. Thanks for watching.